In lesson 1.5, we're going to take a look at a certain type of limit that was first talked about at the very end of lesson 1.2, and that's infinite limits. An infinite limit, just to remind you of what you saw back in 1.2, is illustrated in this picture here at x equals 2. You'll notice if we take the limit at x equals 2 to the left of 2, we would be going down to negative infinity. And if we were taking the limit from the right of 2, we would be going up to positive infinity. And then, of course, since both of those are headed in opposite directions, we would say the overall limit does not exist. But realistically, what we're going to focus on in this lesson is the fact that the left limit was negative infinity and the right limit was positive infinity. So infinite limits are talking about a limit where the answer is turning out to be either a positive or negative infinity. Okay, so let's go ahead and take a closer look at what makes an infinite limit infinite. So here we are trying to take the limit as x approaches 2 from the left of this rational expression 3 over x minus 2. The first thing we're going to focus on is just a table of values, and you'll notice the table of values are values to the left of 2. And you'll notice as we approach 2 from the left, we can notice a pattern in our y values. Again, remember a limit is a certain y value, so we're really focusing on the second row in the table here. So as we approach 2 from the left, I think it's pretty obvious in terms of what's happening here with the pattern. We're going from -6 to -30 to -300 to -3000. So these numbers are getting very big in a negative direction, and I guess in a sense they're getting very small. If we take a look at what's happening to the right of 2 for the same exact function, again you'll notice as we approach 2 from the right, there's a pattern. And in this case, now we're going from 6 to 30 to 300 to 3000. So these numbers are getting bigger in a positive direction without stopping in terms of this pattern that we're noticing. So if we notice a limit that increases or decreases without stopping, or in other words, it's not approaching a specific value, then we can call that an infinite limit. So in this particular case, we can label each of these appropriately. The left limit is going to negative infinity, since those numbers are getting very small, and then the right limit is going to positive infinity, since those numbers are getting very big. As a little bit of proof of that, we can take a look at a graph of the function 3 over x minus 2. You'll notice to the left of 2, it indeed is going down to negative infinity, as indicated by this little rectangular region I highlighted. To the right of 2, you can see that the graph is going up to positive infinity without stopping, and that's highlighted here in this circular shape. What this is really getting us to is a better definition of a vertical asymptote. Just as a little analogy of something you saw earlier with regard to continuity. Up until this point in math, continuity was defined mostly in an informal way because you didn't know about limits. Same thing with asymptotes. You were given the tools to find asymptotes, but you weren't really given the tools to define where an asymptote was happening or why a function was getting an asymptote. But now we can define this a little bit better. If we take a limit to a value, in general could just be a, doesn't matter really what value it is, to the left of a, and we get either positive or negative infinity. And if we take the limit to the right of some value a and get positive or negative infinity, that's what's going to indicate to us that we have a vertical asymptote. Just keep in mind, like with continuity, we might not always either have the ability to look at a graph, or we might not be given a graph for whatever reason in a problem. So now that we're armed with this little definition of vertical asymptote, we can better understand where a vertical asymptote may or may not be occurring. This is not really addressing how you find a vertical asymptote. This is really just more addressing how you know based on a limit if a vertical asymptote exists. Okay, so let's go ahead and take a few infinite limits here as they pertain to these vertical asymptotes. And you can see here we definitely have two vertical asymptotes. So let's go ahead and split the limit at a1 into its left and right side. Here you can see that to the left of a1, our graph is going upwards without stopping, so we can say that limit is positive infinity. To the right of a1, we can see that the graph is going down forever without stopping, so we can say that's negative infinity. Again, now that we know this better definition of a vertical asymptote, just based on this information alone, we can say we know there's a vertical asymptote at a1. But if we want to take this information and determine the overall limit, of course, since positive infinity and negative infinity are going in opposite directions, we would say that the overall limit does not exist. At a2, if we take a look at the limit to the left of that, you'll notice the graph is going down forever, so we can say that's negative infinity. To the right of a2, we can observe that the graph is going up forever, so that would be positive infinity. Again, just based on that information, we know that there's a vertical asymptote. If we want to find the overall limit, again, just like the previous one, these two values are going in opposite directions. They're not coming to a specific value. So in this case, we can say that the overall limit at a2 does not exist. In this graph, we're going to try to take the limit at 0. So if we take a look at just the left of 0 of 1 over x squared, you'll notice that the graph is going up towards positive infinity. If we take a look to the right of 0, again we'll notice that the graph is going up towards positive infinity. Just like the previous example and just like what the previous slide mentioned, based on that information, we do know there's a vertical asymptote at 0. But if we want to come to a conclusion in terms of what the overall limit is, since both of our fingers or the graph is headed in the same direction for the left and the right limit, we can say that the overall limit is equal to positive infinity. So infinite limits, graphically at least, are pretty straightforward. It's just kind of what we've been practicing since we were introduced to this idea of limits graphically. So I guess really the question is, what if we take a limit analytically like you saw in the last lesson? This was brought up in the last lesson where we took a limit, and after we evaluated that function at that limit, we got a value that was undefined. And then I had mentioned that it would take 1.5's lesson to figure out what the final answer would really be. And now we're ready to address that. If we take a limit after direct substitution and we get an undefined value, in other words, a 0 in the denominator, then we know that the answer is going to be positive infinity, negative infinity, or d and e, just like the examples you see above. But we're going to be doing this without a graph. So how are we going to determine, based on this undefined limit, whether it's one of these three answers of positive, negative infinity, or d and e? Well, what we're going to have to do is split the limit into its two pieces, just again like we're approaching it here above, but with a graph. We're going to take the limit to the left of the value in question, we're going to take the limit to the right of the value in question, and then determine those results. The way we're going to do this, because again we're approaching this without a graph, is we're going to consider a number close to the left of that value that we're trying to take the limit at. So if we're trying to take the limit at 0, we would want to consider a value very close to 0 to the left of it and plug that in. Of course, we can't plug in 0 because we're getting an undefined limit. To do the right limit, it would be the same idea. We'd consider a number to the right of the value in question and plug that in. Again, we can't plug in the limit value of a because it's just going to give us an undefined value. So this will be better illustrated in a couple examples in the next slide, but that's the approach whenever you get an undefined limit. Okay, so let's go ahead and take a look at finding limits analytically, but for these infinite limits. So you can see here we're trying to find the limit to the left and to the right of 0 for 1 over x. And you can see right away if we were to plug in 0, we would just end up with 1 over 0, which is undefined. And we need to come to a better answer, as you saw in that last slide. So as was mentioned in the last slide, to do these types of limits, what we need to do is consider a number just to the left and just to the right of the x value in question. And when I say just to the left, I mean very, very, very close to 0. So to kind of better illustrate that visually here, I'm going to consider plugging in the number negative 0.0001. But realistically, it's not really 3 zeros that I'm imagining here. I'm imagining a lot more zeros. It's just a little unreasonable to actually write all that out, but what this value is taking the place of is really just a bunch of zeros and then a 1. Because again, we want to get very close to 0, but not get to 0. So of course, it's not really reasonable to write out 100 or 500 or 1,000 zeros and then a 1. So really just look at this number here as just taking the place of that super duper small number that's close to 0 from the left. So then what is that equal to? Well, I think the best way to illustrate what that might be equal to is just to take a look at a pattern in a table in terms of plugging in these values. Also, as another note, a value to the right of 0 would just be the positive version of that, so 0.0001. But again, there's really many zeros and then a 1. So if we take a look at a pattern here in terms of 1 over x, if we were to plug in the value of 0.1, which is close to 0, but not quite close to 0, we would get a fraction that's equal to 10. 1 over 0.1 is 10. If we were to plug in 0.01, which is getting a little closer to 0, we'd notice that our fraction turns into 100. If we plug in 0.001, that fraction turns into 1,000. If we were to plug in even more zeros, it's going to turn out to be 1,000,000. And you can imagine, if we plug in even more zeros than this, it's going to get even bigger and even bigger and even bigger. In other words, what we're trying to observe here, and of course this lesson is called infinite limits, as that x value approaches 0, in other words, as that x value gets smaller and smaller and smaller, as it gets closer to 0, our overall fraction gets bigger and bigger and bigger. And that value, or that concept that we're approaching, is infinity. So if you take a look back over here at our two left and right limits, it turns out that 1 over negative 0.000001, and again, there's really more zeros than that, is getting us to the idea of infinity. So here we'd be looking at negative infinity for the limit to the left of 0, and we'd be getting positive infinity to the right of 0. So it's very important to take away from this little table here that what we're really seeing is that as this value approaches 0, our overall fraction is getting much bigger, and that idea, of course, is infinity. Now that we have the left and the right limit sorted out, we can of course say that the overall limit is dne, since both of those are going in opposite directions. As some proof of what's going on here, if you graph 1 over x, you can indeed see to the left of 0, we're going down to negative infinity, and to the right of 0, we're going up to positive infinity. So the one thing to take away from this example, and especially from the table, is this idea here, a very important thing we're going to use frequently throughout this course, and it's this idea. If we take a number, it doesn't have to be 1 like it is in this case. A number could be 10, 20, 30, a billion, it really doesn't matter. If we take a number and divide it by a very, 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 very small number, and again, realistically, it's just a number we really can't write. So here we're really talking about these two values, 0.0001. But again, remember, there's really many more zeros than that. Ultimately, that's getting us to this idea of infinity. Any number divided by some very, 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 very small number is getting us to this idea of infinity. And again, if this is something you're having trouble conceptually understanding, take it back to this table here just to understand what's happening to a fraction as the denominator gets very small. As the denominator gets very small, the overall fraction gets very big. Okay, so let's take a look at another example. Here we're trying to find this overall limit for 1 over x minus 1. And you can quickly see here that after we do a direct substitution, we get 1 over 0, which is undefined. So we have to go to our last resort, and that is split this limit into its two pieces, the left limit and the right limit. So again, to overcome these infinite limits, at least without a graph, what we have to do is to consider a number just to the left of the x value in question. Here we're trying to take the limit at 1, so just to the left of 1 would be a number like 0.99999. But again, just like the previous example, there's really a ton more 9s here that we really can't write, which is indicated by the ... So what we really need to do is not put the 0.999 there. If you really think about it, we know this answer because it's an infinite limit is either positive or negative infinity. So what we really need to address is just what are the signs of the numerator and the denominator. Again, since we know we have this undefined limit, which makes this an infinite limit, we really just need to address whether the fraction will be negative or positive, which will then give us whether the answer is negative or positive infinity. So of course, 1 in the numerator is always positive. This is positive 1, so of course I don't really care so much about the number 1 here. I just know that it's going to be positive. In the bottom, if we were to plug in 0.999999 and a lot more 9s here, ultimately we would notice we're taking a smaller number minus a bigger number, which gives us a negative number. But it's a negative, very small number. And again, I'm trying to take this fraction back to what you saw above here. If we take a number and divide it by a very, very, very small number, that gives us infinity. But in this case, because of this negative symbol, it's going to be negative infinity. To the right of 1, it's just like to the left of 1, except we're going to pick a number just to the right of 1. Here, that number would be something like 1.00001. But realistically, there's a lot more zeros than we really can write down on paper. We're just trying to grapple with the idea of what is this infinite limit approaching in terms of it being positive or negative. So again, 1 in the numerator is always positive, so I'm going to indicate that with a positive sign. If we were to plug in 1.00001 into the denominator, when we do that arithmetic, of course we're taking a bigger number minus a smaller number, so we get a positive answer. But again, that positive answer is a very small number. Once we see that it's a positive divided by a positive, again, we already knew this was an infinite limit, so the answer would be positive infinity. Now that we know the left and the right limit, we're ready to answer the original question over here of the overall limit. And since these infinities are going in opposite directions, we can say the answer is D and E. And again, just like most of these problems, I want to give a visual proof of why this is true. And you can see there's a vertical asymptote at 1. To the left, it's going down to negative infinity. And to the right, it's going up to positive infinity. In this slide, we're going to take a quick little review at actually finding vertical asymptotes. What we addressed in this particular lesson with regard to calculus is how we can better define a vertical asymptote. But of course, we still need to know actually how to find a vertical asymptote. And then built into this is this idea of vertical asymptotes versus holes. So these are the 3 steps we're going to be using to find where vertical asymptotes are. First thing we're going to do is factor the numerator and denominator if possible. And then if they can be factored, or maybe the problem is already factored for you, we need to cancel something in the top and the bottom that matches. But the key here is we got to cancel factors. Be very careful that you're not canceling terms out. The third step is just to determine where the denominator is equal to 0, and that will be where we have a vertical asymptote. So in this first example, the first 2 steps don't even apply. We can't factor the top, we can't factor the bottom. And here I just really want to illustrate a very common mistake that tends to happen. The x minus 2 is written so that we can understand that x and the 2 are terms. They're not factors. So we can't cancel these 2 x's here. We can only cancel things in the top and the bottom if they're factors. And factors is just another way of saying that the things that are in the top and the bottom are being multiplied. So of course, if I maybe rewrote this as maybe a 2x, let's say, over a 3x, the top has factors because 2 and x are being multiplied. The bottom has factors since the 3 and the x are being multiplied. And then of course you could cancel those x's out. So again, a very big misconception from previous math classes is to cancel terms and not factors. So be very careful with that. These x's cannot be canceled because they are terms. If that's not an issue for you, then the third step is just a nice easy step. We're going to go ahead and take the bottom, set it equal to 0, which gives us a value of 3. And the way we interpret that value is that is our vertical asymptote. X equals 3 is the vertical asymptote. And you can see here as again a visual proof like I've been doing in this lesson, you can see there is a vertical asymptote at 3. So, of course, we could absolutely just take the limit to the left of 3 and to the right of 3, just like the previous slides. But again, that's not really the purpose of this slide. The purpose is just to identify where the vertical asymptote is, not to necessarily prove there's a vertical asymptote using the limit definition. Okay, so there's the first example. There were no holes in this example, so let's take a look at a problem where a hole might exist and a vertical asymptote. So in this case, you can definitely see much different than the first example, and it might mean we definitely need to do some factoring. So hopefully you're okay with your factoring skills. So you might need to go back and look at some of those, but these two are very, very straightforward. In the top, we can factor it to be x minus 2 times x plus 3. In the bottom, we have a difference of squares, and that in this case would be x plus 3 times x minus 3. Again, the key, like I was saying in the last example, is that we only cancel factors. Factors are things that are being multiplied, not terms. So here you can see in the top and the bottom, there's a factor of x plus 3 and a factor in the bottom of x plus 3. So we can go ahead and cancel those out. And like we saw in 1.3, anytime you cancel something in the top and the bottom, that's giving us the location of a hole. So in this case, we know we have a hole. This would be our hole right here. We have a hole at x equals -3. When we set x plus 3, which is what we canceled, equal to 0, that would give us a value of -3, which would be where our hole is at. But ultimately, we're really addressing where our vertical asymptote is. And you can see we actually just ended up with the previous example. Here I was trying to address x minus 2 over x minus 3, and after we simplified the second example, we ended up with the same function. But I guess the key difference here is that we know there's going to be a hole at x equals -3. So of course we still have the same vertical asymptote, which is at x equals 3, so it ends up being the same exact graph, but with one big distinction. Since we canceled that x plus 3 in the top and the bottom, which gave us a hole, we need to graph a hole at x equals -3. So really what you should take away from all of this is just a little review of stuff you've seen in previous math classes. In previous math classes, you were given these rational expressions, and after you simplified them, you would just set the denominator equal to 0, and that would tell you where a vertical asymptote is. And then on top of that, if you canceled anything in the top and the bottom, that would also indicate that you have a hole in the graph. In this slide, we're going to continue where we left off with the last slide, and that is just identifying these types of discontinuities, specifically holes and vertical asymptotes. Here we need to find the values of x for which this function is discontinuous, and then identify the type of discontinuity. After we do that, we can sketch a little graph of what's going on. So here, just like what the previous slide mentioned, before we even address anything, we need to try to simplify the top and the bottom, specifically by factoring. Again, if your factoring skills are where they should be, the top and the bottom should be very easy to factor. The top factors to be x plus 4 times x minus 2. The bottom is the difference of squares, x plus 2 times x minus 2. Like you heard me say a couple times in the last slide, we need to be very careful with what we cancel in regards to a fraction. If we have terms, which are things that are being added or subtracted, we can't cancel those. But if we have factors, which are things that are being multiplied, we can certainly cancel those. And here you can see in the top and the bottom, we have a factor of x minus 2, which means we can cancel that, and that already tells us we have a discontinuity. And that type of discontinuity would be a hole. Since we're trying to graph this, it's really not enough right now just to say x equals 2 is where the hole is at. Sometimes that'll suffice for a problem, but since we're trying to really sketch a graph of this, we also need the y value for that hole. So of course, to do that, we would just take the 2, plug it back into this function here of what was left over of x plus 4 over x plus 2, and then that gives us a y value for f of 2 of 3 halves. So we know we have a hole at 2, 3 halves. Now that we've addressed our hole because we had something in the top and the bottom to cancel, we can now tackle the vertical asymptote issue. If there's going to be a vertical asymptote, and there might not always be, that would be when the bottom is equal to 0. So of course you can see here nice and easy, and again I'm labeling this as a vertical asymptote since we need to identify these types of discontinuities. The vertical asymptote would happen when the bottom of the denominator is equal to 0. Here that's at x equals -2. So to finalize the first part of this question, we just needed to identify the discontinuities, and of course we have a discontinuity at x equals 2 and at x equals -2, and then on top of that we've identified the discontinuities as our vertical asymptote here and as our hole here. Once we've done that, we can just take some of this information and get a rough sketch of what's going on here. Of course, we would draw our vertical asymptote at -2. We would draw our hole at 2, 3/2, and then ultimately we get this picture that describes this function that we were originally given. Again, we could easily take the limit to the left, which would be -infinity. We could take the limit to the right of -2, which would be +infinity. And then, of course, we could validate why we have a vertical asymptote there to kind of better understand the definition of our vertical asymptotes using limits. Okay, this last slide of chapter 1 is just going to serve as an overview of the different ways we learned how to find limits here in chapter 1. The first way we learned how to find a limit was visually using a graph. The way I introduced that to you was just using your left finger to the left of the point, your right finger to the right of a point, and bringing your fingers together to see what was happening to find that y value, which was the limit. A little note to make here would be to be very careful. Using your fingers to find limits visually is definitely a nice easy way to approach it, just to make sure you're always getting the right answers. But if you encounter a problem that asks you to justify your reasoning as to why a limit exists, just be very careful you don't use some sort of justification based on your ability to use fingers on a graph. Just keep in mind we need to say something about the left limit versus the right limit. Another way we saw limits in this chapter, not a lot, but a few times, was taking limits numerically with a table. Really, this is the idea that we're using graphically, but without a graph. What we're trying to do is to find a pattern in these y values in the table to come to a conclusion as to what's happening with the limit. The last way we saw in terms of taking limits was in 1.4 with that idea of direct substitution by plugging in the x value to see what happens. And there were a few cases that we got after direct substitution. It didn't happen a lot, but there were cases where if you plug in the x value, you would just get some other number as the answer, and that would be what the limit was equal to. In other cases, we got a value where it was 0 over a number. Of course, 0 over a number would give us the value of 0, so that would make the limit equal to 0. As you saw in this lesson, if you ever have an undefined limit where we have a number over 0, that just tells us we're going to have this infinite limit, either positive or negative infinity, or possibly dne, which of course also meant there was a vertical asymptote. The last type that we got analytically was 0 over 0, like we saw in 1.4, which is another way of saying an indeterminate form. Once you encountered that version of analytical direct substitution limit, you just need to know that you need to do more work so that you can retake the limit and see if that gives you a value after that. Ultimately, what you need to take from this entire chapter is this very important concept of a limit, because as it pertains to our second chapter, and really the first big hurdle we have to overcome in calculus, is applying that limit to one of the most important ideas that you're going to study in calculus. But we'll take a closer look at that when we start chapter 2.